Hello, everyone. Welcome to another VTSS seminar. Today we have Stephan Smeekes from Maastricht as invited speaker and Giuseppe Cavaliere from Bologna and Exeter as guest panelist. Stephan, the floor is yours.
Thank you, Adriana. Thank you very much for inviting me. I'm very happy to present here. So the paper I will present today is called Inference in Non-Stationary High-Dimensional VARs. And it's joint work with my colleagues one from Maastricht, Alain, and my colleague from Lund, and formerly Maastricht, Luca Margheritella. What we're going to do in this paper is look at doing inference in large time series models, and specifically focusing on Granger causality testing. So informally, the kind of question that we would like to answer is, if we have a time series of interest, let's call that YT, does it help to predict that time series if we know the past of XT, another time series? So can lags of X help to improve predictions of YT? Now, of course, that is given a certain other set of information. In particular, we assume that we have a set of time series available, and denote them by boldface WT, which we want to condition on in this analysis. If we want to write it more formally, we say, well, we have a certain information set, which is the history of all these time series WT, and given that particular information set, does it help to add X, the time series X, to the information set in order to predict Y? Of course, the way we should interpret the Granger causality highly depends on the way you set up your information set. If you just do a standard bivariate case where we don't have actually any other series in W, we're looking at a very different relation than if you would have a very large information set. And if you go back to the original paper by Granger, where he envisions the information set to be all of the information in the universe, that's of course a very different thing than just a bivariate test. Of course, all the information in the universe is very difficult to actually gather and fit into your model. But there are still good reasons to look at a large number of time series. And that we would then end up in a high-dimensional setting as we are looking in our analysis. First of all, the application itself can dictate the need to have a large information set. And that's actually the setting that I will consider here in this presentation when I discuss the application of our method. An alternative motivation can come from the use of Granger causality testing to establish networks of connectivity among different time series. It's particularly often done in a financial context, where we can simply create a network by drawing an edge from X to Y if indeed we find that X Granger causes Y. And then people use these networks to study how things are connected, spillovers, which financial assets, for instance, can be grouped together, and so on. So as a small illustration why the choice of information set matters, let me go back to a previous paper in which we considered the same problem, and we investigated there, well, what if you would do sort of the Granger way and put all the information of all your assets into your information set. In our case, those were 30 assets, and we had realized volatility of those. Or you do just bivariate tests for every pair, check if there is Granger causality. And I just report the plot from that we had in that paper, and you see on the left is the result where you do all the bivariate tests, and basically you do not see anything because all of the assets, all of the yellow circles on the outside are all connected to each other. Now, if you put all of the assets into one big system and you do the Granger causality based on that, so we are conditioning every time for every pair on all of the other 28 assets, you get a much clearer picture, which is, I think, another reason why it's often can be very meaningful to consider a large information set. And there's been quite a lot of work in recent years, among which the paper I just mentioned we did earlier, where people have been looking at constructing methods that we can do for doing inference in these big time series models for Granger causality. So what we're going to do, which is very common in this literature, is we're going to assume linearity, in which case we can use vector autoregressive models to investigate this by simply testing the significance of the coefficients of the lags of your series X in the equation where we model Y. If we indeed have this big information set, we will need to look at high-dimensional methods. There are many ways in which you can do a high dimensionality. What we are focusing on here is a very common framework of sparsity. So we are assuming that in all of these relations between all the series that we are interested in, there will be many zeros in these coefficients. There is sparsity. We don't know where the zeros are, but they are there. And that, of course, brings us to the kind of typical ways to estimate such models using penalized regression methods like the lasso. And there's now been a lot of work on estimation of sparse VAR models, but also of doing inferences in sparse VAR models. I give a few papers here, which is a very non-exhaustive list. There's, of course, much more out there. And the paper that this current work is based on, also a joint work with Alain and Luca. It's now out in the Journal of Financial Econometrics. There we do essentially this. We look at Granger causality testing in sparse VAR models, and we make sure that we have valid inference results by applying the post-double selection principle originally proposed by Bologna and co-authors. I'll come back to how it works a bit later. Because so far, I've not really been saying anything about what we're doing in this particular paper. So here's the key contribution of our paper. All of the methods that I mentioned before, in particular also our own method, relies on stability of the underlying VAR. In many economic settings, of course, one particular form of non-stationarity that we would want to account for is having stochastic trends. We know there are unit roots, we know there's co-integration, there might be even series which are integrated of order 2, so we would need to difference them twice to achieve stationarity. So typically what we would do in this kind of analysis with these big VAR models is we first difference everything before we do our analysis. So if we know that there's a unit root everywhere, we take first differences. If we think series are already stationary, we don't do any differences. There are a number of reasons why this is problematic, and in particular, it's even more problematic in high dimensions. First of all, by removing the trends from the data, we are not accounting for co-integration. So if the different time series share their stochastic trends, there are long-run relations between them, which obviously implies some form of Granger causality, but by differencing them, we remove them actually from the data. So the question is, if we're testing for Granger causality, is it actually still the same causality that we're testing for? The second, more practical problem is that it's often not so easy to find the right way to difference your time series. We can, of course, do unit root tests, but obviously unit root tests are not infallible. So you can get wrong results. You can even, if you apply different unit root tests, you can get different results. And that can even be up to very small things as changing the way that if you do an ADF test, the lag length is selected. So we can make mistakes, and the more series we have, the more decisions we need to make on how many times to difference. So the more the classification errors that you make in classifying them as I1 or I0 quickly accumulate. And finally, also then the interpretation of Granger causality is changing, because suddenly we're not, if we difference one series but not the other, then we're testing a different way of predictability. We're testing from differences, or testing if you have loss from growth rates rather than levels. And it's not ideal that like the statistical properties decide on how you should interpret your results. That, in my opinion, that would rather be up to the researcher. So what we do in this paper is to build on our previous work and extend that to a test for Granger causality in high-dimensional VAR models that works in levels, irrespective of the order of integration of the underlying time series. We don't need to know, and we also do not need to model that. And the tool that we're going to use is, so in a way, something very simple, is the so-called lag augmentation approach originally proposed by Toda and Yamamoto, where they say, well, if you simply add an additional, essentially redundant lag of your variables to the VAR, you can eliminate the influence of the order of integration. As it will turn out, of course, in our setting, just adding a lag is not so straightforward. Otherwise, of course, we would not have to write this paper about it. So in the remainder of the talk, I will explain what exactly we do, how we make this work in our high-dimensional setting, and why we think this is a good idea. Let me quickly introduce the data generating process that we are looking at. As I already mentioned, we're going to look at VAR models, and we're going to look at VAR models of dimension k. So k is the number of time series, and we think of that as typically being large. We're going to assume that there are p lags in our model, so it's a VAR of order p. And for now, I am going to assume that p is known, which obviously is not the case in practice, and we will need to deal with that. But for the first part of the talk, it's helpful to assume that it is actually a known quantity. Where the typical assumption would be that the roots of the matrix polynomial of the VAR coefficients would lie outside the unit circle, we also allow it to lie on the unit circle. And therefore, we allow for unit roots and possible co-integration. In our big series, bold-face set, we have two series that are of interest. Y, which is the series we want to predict or investigate Granger causality towards. And we have X, the series that we want to see if that one actually can help in predicting Y. And then we have the other series, the information set. You can also think of them as control variables if you want. I'm going to focus here on a single variable of interest for Y and X. We can extend it to blocks as long as these blocks are not too big. So if you would have multiple series there, you can do it, but the notation becomes a mess. So I'm going to stick with one series each. In the already published paper, we do it for blocks. So if you're interested in how to extend that, have a look at that paper. If we write out the VAR model, of course, we have a bunch of coefficients in our matrices A, and then we see that actually it's one coefficient in every matrix that is of interest. It's this element, which is the coefficient of the lag of X onto the equation of Y. And if all of those are zero, then we know that, well, the lags of X do not affect Y, and therefore we know that there is no Granger causality. So in the VAR model, the null hypothesis of Granger non-causality simply reduces to the null hypothesis that all of these coefficients in red are actually equal to 0. And this is then what we're going to test. And so in fact, we only need the first equation of the VAR. And we can write it then simply as a linear regression model. So we do the regression of y on the lags of x, denoted by xt minus p, as well as all of the other variables, the lags of all the other variables, which is the lags of y itself, plus the variables in w. And in this regression framework, we simply test whether beta is equal to 0 versus the alternative that is not equal to 0, and that will be our test of range and causality. Now, of course, if the number of variables is large, then the number of regressors here is simply too large to estimate this by OLS. Well, there are, of course, many ways to deal with high dimensionality. As I mentioned, what we're going to assume is that there is sparsity. So we are going to assume that in the VAR, and then, of course, as a result, also in the equation here on the slide, many of the coefficients in delta are actually 0 or close to 0. But, of course, we don't know which ones they are. And so what we do is we estimate that by the lasso. So you don't necessarily have to use the lasso. You can use any of its variants as long as it's some form of regularization that gives you variable selection. So we want to remove the variables that are not important, essentially from the regression. So one thing you could simply do is to estimate this regression here, say by the lasso. You will get a set of variables that the lasso deems relevant. You could remove all the other ones that are not relevant and then simply, for instance, re-estimate the resulting model with least squares and do your standard form of inference that you would want to do your wall test or LM test in order to test the null that beta is equal to 0. It's well known in the literature that this is not a good idea, as this will not lead to uniformly valid inference. So the problem in that case is that we have in our delta, we could have coefficients that I call them smallish. So they are relatively small, such that your regularized estimation, say your lasso, is not able to detect them. So it will kick those variables out, but they would still be large enough to cause omitted variable bias. And that, of course, is a problem. So that's definitely not what we want to do. Again, this is not something that is new, that we came up with. It's in the last 10 years, there have been many developments in coming up with inference methods that allow you to circumvent that problem. And one way is the post-doubled selection proposed by Bologna and co-authors, where we take the perspective of first doing partial regressions. So you can think of it in the sense of the Frisch-Schwab-Lowell theorem, where we regress both the regressant as well as the regressors of interest, so y and the lags of x, on all the other variables first, all the variables in V, so that's the lags of y and the lags of w. And what we then do in the post-double selection is we collect all of the variables that are deemed relevant in these initial regressions. So again, we can estimate these using the lasso or whatever your favorite penalized estimation method is. Again, the only thing you need is to make sure that there is a variable selection mechanism in that method. So you select every variable that was chosen by, say, the lasso in these initial regressions. We put them all together, and then we add all of those. We add in our final regression. So in our final regression, we, of course, consider still our x's, but we also now consider all those variables that were selected in these initial regressions that we do beforehand. This is enough to restore asymptotic normality to your estimator of beta. So you can estimate this one with OLS. And the reason why this works is that we are now, in a way, giving our regularization method a second chance to get things right. So it can make a mistake. So if you have small coefficients, it might still miss in this first regression where we do y on all the other variables. It might still miss that factor. But if we also miss it in the regressions on the lags of x on all the other variables, then that would mean that not only the coefficient is small, but also the correlation between x and this particular variable. So even if we miss it, it's not going to be correlated with the other regressors and therefore will not cause omitted variable bias. So if either the coefficient is relatively large or the correlation with x is relatively large, then our method will pick it up. And only if both of them are large, actually, it will cause a problem. So this works relatively straightforwardly to deal with that issue. Again, this is what we did in the previous paper, and we still need to account for the fact that our series might have unit roots. So first, let me introduce a bit this lag augmentation idea to see also what it does and why it works, because it's a very simple trick. So let me take a very simple setting first, where we just do a regression. We have two variables only. We have y and we have x. And we're going to want to estimate this simple regression model, y on the first lag of x. And x might have a unit root. So the coefficient rho might actually be equal to 1. But we don't know. We don't know if it has a unit root or not. Let's assume that the error terms are actually well-behaved stationary error terms. And of course, the most basic thing is just estimate this by OLS. We get our standard OLS estimator. And then we know that the properties of this estimator depend on whether there is a unit root or not. Is there no unit root, then everything is fine, everything is standard, and our estimator will be normally distributed asymptotically. But if there is a unit root, then we have to deal with all the issues there. We get all the horrible functionals of Brownian motions, and our inference is distorted. It's fine if we know that x has a unit root, but if we don't know it, then, well, we actually don't know which situation, of course, applies. So what Tora and Yamamoto said, well, just add a redundant lag to your regression. So here we would add xt minus 2, even though we know that in truth the coefficient of xt minus 2 is 0. So we just add xt minus 2. We then have a regression on xt minus 1 and xt minus 2, and we can simply estimate this by OLS. And then the key is what they say to do is to then only do inference on beta 1. So we basically ignore beta 2. We're not interested in it. We only do inference on beta 1. I mean, why would this work? It's still just OLS. Well, if you write it down in terms of a partitioned regression, you can already see why things might work. Because now if we look at this expression here, then in a way, by the fact that we are now first would regress xt minus 1 on xt minus 2, which is this rho hat coefficient, and we take the residuals of that, in a way, this might eliminate the potential unit root in x. So it might actually indeed be that this would work. As I will show next, in fact, it does, and we can even get a stronger result. Well, one simple thing you could simply do if we take our augmented regression model is we plug in for xt minus 1. Just plug in by the fact that we know it's rho xt minus 2 plus the error term. Well, rewrite things a bit, and what we see is that if we would know u2t, we could actually do the same regression. Instead of on xt minus 1, we would do it on u2t minus 1, and this coefficient is still in truth, because beta 1 is just equal to beta, would just be beta. So doing this regression, we would do inference on the same coefficient beta as if we would do it on xt minus 1. And we also know that this error term is well behaved at stationary and would allow us to circumvent the unit root issue in that sense. But of course we can't, because it's not actually observed. But still, if we work out the math, in the end, what we can show is that your estimator would, if there is a unit root, all of the unit root stuff will actually drop out, and you'll end up with some nice, well-behaved estimator consisting only of stationary quantities. So this would give you a normal distribution. Final step, we know it's unobserved. It turns out that we actually don't need to observe it. If we just think about the regression estimator rho hat, which I defined here, which was the partial regression of xt minus 1, xt minus 2, well, we can simply write it as the true rho plus the regression estimator in the of u to the on xt this one. Well, this should all be shifted back one period. The one that we are actually going to use here. Well, simply plugging that in, plugging again in the definition of xt minus 1, gives us this expression here for our original beta hat, which then turns out to be identical to the beta 1 hat, the infeasible one that we got from this regression that we actually, we cannot do in practice. So it turns out that just a very simple thing of adding this lag here, and turns out that it allows us to essentially implicitly do this regression, that where there's no unit root anymore. There is a unit root here, of course, but this one doesn't matter because we're not interested in these coefficients. We're only interested in this coefficient. So this free lag, this redundant lag, in a way allows us to create an automatic differencing system without actually doing that implicitly. Note also that if there was no unit root to begin with, we're not losing anything. I mean, this still just is a well-behaved regression model then. So we don't actually need to have knowledge of whether there is a unit root or not.
Stephan, can I ask a question?
Yes, sure.
So these greater causality tests are used a lot in financial econometrics in predictive regression framework, and there you have essentially two issues. One is that you don't have unit roots, but probably you have roots local to unity, or you don't know exactly how these roots are, but essentially one of the problems is roots which are local to unity, and the other problem is this endogeneity between, so correlation between the innovations of X and the innovation that appears in the regression equation. So I'm wondering if these kind of issues appear in your framework or not.
They do not matter. No, I'm focusing here on the unit root case, but if you would have local to unity, you have exactly the same result. So it just depends on the stochastic orders, which would not change. So you have the same result, in particular the fact that this xt minus 2 that will not have an effect, it will drop out. That remains valid also for local to unity. You do indeed have to add this additional lag to make it work, but that will deal with that problem. And we don't say anything about correlation between the innovations. That's completely free.
Okay, excellent. Thank you.
Can I also ask a question?
Sure.
Helmut Lütkepohl is my name. If you have higher order unit roots, seasonal unit roots or something like that, then this one leg wouldn't be enough, right?
No, then it would not be enough. So we're not looking at that explicitly in the paper. We look at I2, which then of course you need 2 legs to add 2 legs, but then you would need to add, yeah. So in general, you would then need to add more. So in principle, the idea that we have is not necessarily restricted to how many legs you would need to add. Basically, if it exists in low dimensions, then you can do the same idea in high dimensions. So I think in that sense, what we are proposing here, I'll come back to that in a second, is not really, let's just say what we do in high dimensions is not changing anything that would be applicable already in low dimensions. And so what we would do in low dimensions is we would simply add the lag of all the variables to your VAR. In this case, to the one equation of the VAR that you need to estimate. We add them when we do the estimation, but we just test it on the first coefficients, the original ones. And as I said, if you have higher orders, you need to add more lags. So this is all fine. And there are many papers which use this idea. There's also recently it has been used for impulse response analysis as well. And so what we want to address here really is how to extend this to high dimensions. And there we need to answer two questions. The first one is, how do we combine the idea of lag augmentation with the fact that we're not just estimating one regression, but we're doing these selection steps? And the second is, how do we deal with the fact that in high dimensions, well, just adding all of the variables, the lags of all the variables will simply not work because we add too many parameters to estimate. Well, first of all, the nice thing about this post-double selection framework, and that we can split our high-dimensional inference in multiple steps, is that we can just do the lag augmentation in the final step. And this is also why everything that is valid in low dimensions transfers here to high dimensions, because in the selection part, the initial regressions of y and x and all the other variables, we don't consider any lag augmentation, so it doesn't play a role there. There's another issue that we do need to be careful with, is that we could end up with spurious regressions because we're not estimating the full VAR, but we're only estimating parts of them. And the solution to that is simply to not leave out all the x variables from your initial regressions, but put them in. So we put them in to avoid spurious regression, and we show that actually still leads to the same valid inference. And you can even decide not to put any penalties on these variables, particularly on the x and the y's, to really make sure you will not end up with something spurious. It's also a bit trying out what works best. We find that being careful actually does work quite well. There could still be an issue that if you don't have enough lags in your system, you might still end up with a spurious system. Imagine we would only include one lag of x. Then when we do this partial regression on that one lag, there's no other lag that we actually have left. So this term would be empty. And of course, that could still be spurious. So in that case, what you can do, what we'll recommend is make sure that you choose P large enough, so at least add 2 lags. That would solve the problem here. Or you could just add an additional lag to your selection regression, which we investigated at least in small samples, and that also seems to avoid any issues there. And then for the second problem, that we cannot add lags of all the variables, there we actually have a very simple solution. Because what we show is that it is not necessary. If we're only interested in the coefficients of the lags of x, we only need to add lags of x to your regression, and not of any of the other variables. And well, then instead of having to add, if we have k variables, k lags to our final regression, we only need to add one variable, so one parameter additionally to estimate. So it might be something that even in lower dimensions where you can still use OLS, this could be worthwhile to do to gain some power. So our estimation algorithm then simply looks like this. We do your initial regressions. Just make sure you put your x's in there as far as you can. And then you add just only these additional lags of your x to your final regression. The rest stays the same. You still collect all of the variables that are deemed relevant in these regressions in this part here. And then you can use whatever methods you want to test whether this beta factor is indeed equal to 0. So in the paper we look at the LN test and the wall test, and in the work that follows, everything is based on the LN test. Let me very quickly go over the kind of conditions that we use to prove that this indeed works. So we assume rather high-level conditions, which on the one hand is nice because it allows quite some generality in, for instance, what kind of regression, penalized regression method you use. On the other hand, they are a bit more difficult to interpret. So we'll just quickly go through them. Well, first we need like pretty standard assumptions on the innovations of the VAR, because we need to have appropriate CLTs go through. You can allow for heteroscedasticity, for instance, as long as you just correct your test statistics there. In the paper, for simplicity here, we don't do it. We did cover it in the first paper. Of course, the key setup, otherwise nothing works, is sparsity. So we do need to have sufficiently sparse parameter factors, not just in the original regression, but also in the selection regression. Or alternatively, we can impose those conditions on the VAR itself, which is a more natural thing to do. And so we simply need that there are not too many variables, like a slowly growing ST number of them, that are actually relevant. We can we assume exact sparsity here. You could extend it to have like very small coefficients. For simplicity, we don't go into that direction. And then we need to have some typical Lasso style assumptions. So we need to control the tails of the empirical process, where the empirical process is the matrix Z, which collects all of the regressors times the error term U in the regression, the equation of the VAR. And what we need that here, what's special here is that we need it in a like rotated form. So we need to, if there is, for instance, co-integration, then we need to rotate our variables to get the pure unit root and stationary components separated. We do that using this Q matrix. Actually, proving these bounds for non-stationary data with unit roots is rather complex. We don't go into that in the paper. Here, there are some results in the literature where these bounds are proven. Admittedly, I think the results are not super general yet, so this is certainly a work that requires further attention in the future, but clearly it's not something that we can solve in this particular paper. Another typical assumption is a form of restricted eigenvalue condition, where we need to make sure that smallest eigenvalue of the ground matrix is bounded away from 0 with some high probability. It doesn't have to hold for the full matrix, which is high dimensional, but as usual, it holds only for some subset of it. Essentially, we have some sparse factor that we multiply it with, and for that, it has to hold. Again, there's a whole lot of technicality going on to establish these kind of assumptions. Here, we just assume that these results exist. There are, again, some results out there. It's tricky for data with unit roots. And we do not get the standard rates that you would get for stationary data, even if you already account for the fact that we we normalize differently, so we have a different rate of t that we normalize with, but even then, you still need to inflate the rate to make it work, but it is possible. Of course, what we need as a key component is that the estimator that we use, the lasso type estimator in the selection regression is, well, it should be accurate in the sense that in terms of prediction accuracy, it should be well enough, but also it should be sparse enough. We cannot select too many variables, already for the simple reason that, well, we need to do OLS on the final step. And if we do OLS on the final step, well, we cannot have too many variables in that equation. Now, there is, thankfully, there is, so this is, of course, a very high level assumption. But again, if you assume the previous conditions, in particular about the empirical process and the restricted eigenvalue, well, with those, you can get very far in actually showing that this holds. And then finally, we have all of these rates for the eigenvalues, for the tails, and for the error bounds, and these need to, of course, add up. What it in the end reduces to, based on the current state of the literature, is that as long as the sparsity is not growing very fast, so ideally it's not growing at all or very, very slowly, so the number of relevant variables is close to being fixed, it helps if the innovations in the VAR are well behaved and have thin tails. I mean, sub-Gaussian would be great, or at least sub-exponential. Then it works for reasonably high-dimensional processes. So we can then definitely allow the number of variables k to be at least of the magnitude of the number of time observations. Again, there's always this trade-off. If you allow for fat tails, you can do that, but it will then put more restrictions on how large your system can be. When we use this in our asymptotic analysis, we have two steps. And the first step, there's no lag augmentation. It's simply showing that, well, instead of the selected variables, if we would have the true ones, we'll end up with an asymptotically equivalent estimator of the betas. So there's no lag augmentation there. And then once we have that, then comes the lag augmentation in, where we show that, you know, doing just adding the lags of x will give you asymptotically normal inference. And it's also this separation why I think that everything that works in low dimensions can be applied in high dimensions, because the first part is a really high dimensional thing, and the second one is not. Let me very quickly look at some simulations. I will not bore you with tons of tables. We look at two very simple VGPs, VAR1. Well, one is really a basic case where everything is diagonal, so it's just a bunch of AR1s. The second one is not diagonal, and here we have decaying coefficients the further the variables are apart. We look at size and power, so we manipulate this one coefficient to set either 0 or 0.2. And well, we assume normally distributed error terms. So again, we can allow for some correlation between the different error terms in the VAR. And we just do lasso, very simple lasso, Turing parameter chosen by BIC. And we do some ad hoc upper bounding of the number of variables we allow to be selected in cases where there would be too many. And we did this already in the first paper, and that seems to work quite well. This is only one of two tables that is in the presentation. I think the main message is that size is quite okay. If t is small, there is some distortion. The size is a bit too high, but it really seems to be just a small t effect and not so much an effect of high dimensionality, because increasing k does not make things worse. And if we make t bigger, we quickly go towards nominal. Power is difficult to interpret. I mean, the one thing we can see is that at least the patterns make sense. If t becomes bigger, your power increases quite a lot. If k becomes larger, your power decreases somewhat, which is also natural, but it's not very dramatic. Same for the if we allow for correlation among the innovations, size gets a bit worse because I mean this is just not that sparse DGP anymore. But still, it seems to be quite okay. Let me address the final issue that we need to address, and that is how to choose the lag length. Because I've so far assumed that we know it, and this is not realistic, of course, in practice. There might be applications where you have a good idea of how to choose it, but I think in general it is not. So one thing people typically do with lasso kind of methods is to just say, well, we just set it to a very large number. We just include many lags, and then we'll let the lasso decide because, well, if coefficients are not relevant, if variables are not relevant, coefficients of 0, then the lasso will kick these variables out anyways. For us, this does not work because, I mean, suppose we would just say, well, we set p equal to 25. It does mean that in our final regression, our regression after selection, where we use OLS, we need to include all of these 25 lags of x, plus then the 26th lag to do the lag augmentation. So this is not a good approach. So we need to do something better. There are two options we looked at. One option is to, well, build lag selection into your penalized regression method. For example, you can use the hierarchical penalties of Nicholson et al., who basically say, well, I will only consider including the second lag of a variable if I have included the first lag in my final model, and only the third one if I've included the first and second one. This is something you can do. We found in our setting we had some difficulty getting it to work well, and so instead what we do is, well, not try so much to find the right value for p, but just to find a reasonable value. And that is something that we call an informed upper bound. It's not a problem if we have a lag length which is a tiny bit too high. Well, again, I mean, the lasso can handle it, and it does not really affect our final equation. What we really do not want is to have p too low. If we don't include enough lags, then, right, suppose the true lag length is 3, you only add 2, then you think you're lag augmenting by adding the third lag, but actually that third lag is needed and it's not an augmentation. And what we do there is something very simple. We just estimate univariate autoregressions. And those will give us a very reasonable upper bound of p. So we estimate univariate autoregressions for all k variables, and then just apply an information criterion to that. Again, what we do is we don't even look at we just simply ignore the correlations between the residuals, just look at the variances, and then do an information criterion based on that, and you can choose whatever information criterion you prefer there. We did that in DGP2 to check how it works. Green means that the correct lag length is selected. Blue means you choose too many lags. Light blue is 1 lag too many. Dark blue is more than 1. And red is the worst case where we underselect. So p is equal to 2 is a true lag length. P equal to 1, the red case we don't want. And in fact, it only happens in 1% of the cases in one particular combination of t and k. And nowhere else does it happen. And in particular, BIC just gets it right pretty much all of the time. And the only cases where it selects too many lags is when we have 1,000 observations, and well, we don't particularly care in that case if we have a few lags too many. So this gives us a very simple way to select lag length that for our purpose do a job really well. To round up, let me illustrate using an application. Well, first of all, why we think this kind of gradient causality tests are useful, but also the impact that differencing or not differencing has. And so what we're going to do here is we're going to focus on uncertainty shocks. So there's a lot of literature in macroeconomics about the role of uncertainty shocks in the economy, and people have come up with different ways to, first of all, think of how to measure uncertainty, which of course is not directly observed. So there's the seminal work of Bloom, where he proposes the VXO index, which is an index measuring essentially stock return volatility as a measure of uncertainty in the economy. This was included actually also in the FredMD data set of McCracken and Eng among the many 200 plus time series of the US economy. There's also an alternative measure, the Economic Policy Uncertainty Index, it's now very popular, which is mostly based on newspaper coverage from frequency of terms related to uncertainties. Essentially, it's a word count of how often relevant terms appear in newspaper articles related to the economy. And if we look at these series, well, we can ask a bunch of questions. First of all, we can ask, well, which of these measures of uncertainty would we want to consider? And next question is also, what kind of role does uncertainty play in the economy? So there's literature which argues that either you should see it as an exogenous shock, where it's the uncertainty that is causing, for instance, higher uncertainty would cause a decrease in economic activity. But you can also think of it as the uncertainty is actually a response to changes in the economy. If things are not going well, then uncertainty will increase, and it's not the other way around. And so this is what we're going to use our Granger causality framework to investigate. So we want to investigate, well, if we think of it in terms of predictability, do we observe predictability from the uncertainty measures to all the other series, the macroeconomic series in the FredMD, or is it the other way around? And that would shed some light on whether we should see it as a cause or actually as an effect. And we can also ask another question, well, given that VXO is in the FredMD, at least in the vintage that we are using here, does it still make sense to also look at EPU, the Economic Policy Uncertainty Index? So if we already have VXO, does EPU actually add anything to the analysis if you add it to your data set? And what I'm going to do is to compare then our approach in this paper, where the lag augmented approach to the approach where we first transform everything to stationarity. Apart from that, we're going to use exactly the same method. So it's the post-doubled selection method. Based on LM tests, everything is tuned in the same way. It's just the input data are going to be different. And one reason why we chose this application with the FredMD is because there we actually have a classification code available, provided by the authors, where they say how we should transform our series to achieve stationarity. Which the advantage then is that we can sidestep the whole issue of not agreeing unit root tests. So another paper, we tried different kind of unit root tests, and even like the same test where you think you're doing the ADF test, but implemented in different packages in R, which are all tuned slightly differently, and you just get very different results. So then it's not even clear how we should do all of the differencing. So we avoid that here by using just the classification codes. So this gives us the result for VXO. So here we leave EPU out of the equation. And what I'm showing here, these bars indicate significance. So the higher the bar, the lower the p-value. So it's based on a reverse of the p-value. So if the bar goes all the way to the top, the p-value would be 0.
Sorry, I have another question. You mentioned that this uncertainty index and so on, that is often used in structural VAR analysis, but then you would put in the contemporaneous value. Did you do that here, or did you put in lags only? Did you do the standard Granger causality?
Yeah, we do just lags, the standard Granger causality. We're also not claiming that this is a full analysis. And indeed, I mean, if you really want to properly investigate this, it should be in a structural VAR. What we want to show here is that, you know, this could be one component of the analysis. And the main message that we really have here is, how is it different if you just if you transform everything to stationarity or if you don't? And it actually shows, I think that is shown quite well. I also really do not want to draw any more conclusions than that from the analysis, but indeed, we're of course not looking at contemporaneous relations, which is by far the more complicated issue here.
Okay, thanks very much.
So here in the top line, the top two lines indicate the results for the lag augmentation method. So here we do everything in levels. Well, there's a few observations to make. Again, you should be quite careful. Also, I did not correct any of these p-values for multiple testing, which is obviously happening here. But still, let's just quickly look at the results. And one thing we see is that if we look at Granger causality from all the series in the FRET-MD to VXO, there seems to be quite little. It's only in the category stocks where there clearly is, which is, I think, not very surprising, given that actually VXO is an index of stock return volatility. In the other direction, from VXO to FRET, there is quite a bit more Granger causality. In particular, in the output category, which is where of course much of the economic debate is about, there seems to be quite some significant p-values here. The most interesting part, if we compare it to the bottom part of the graph, where we've transformed everything to stationarity, and you get really a different picture. So there's barely any significant p-values left. In particular, like if you think that, you know, we should correct them for multiple testing, then everything will be gone. And also, like the block of outputs that we observe with the lag augmented method is gone if we transform to stationarity. Also, the Granger causality from the stock indices in the FRET is also gone when we transform to stationarity. So it does seem that this clearly makes a difference, and whether it is because there is some co-integration that is not taken into account properly anymore, or what exactly the cause is, I don't know. It's definitely something that would be interesting to investigate further, but well, it clearly matters. And the same conclusion we basically draw if we look at EPU. So if we now we keep VXO, but we add EPU and we do the same analysis. Again, if we do the lag augmentation, we have a clear block here for outputs where there seems to be something of Granger causality occurring that is disappearing if we transform to stationarity. Another interesting one here is the red bar. So this is actually VXO. So the red bar indicates Granger causality from VXO to EPU and the other way around. And we see that if we do the lag augmentation, the test indicates Granger causality from VXO to EPU. But if we do the transform to stationarity, it's actually the other way around. I don't know what is the right interpretation, but of course it's quite a big difference. And therefore, well, I guess this again highlights the fact that it matters what whether you take differences or not, and how you treat your variables. Okay, let me wrap up here. I think what we've proposed is a very simple method, but it does seem actually quite powerful to get robustness against the order of integration in your high-dimensional system, where it's simply not so easy to get to model everything correctly as you could do in a low-dimensional system. It seems to work quite well in practice, and I think our empirical application shows that it matters that whether you indeed transform everything to stationarity or not. And it's something that you would like to have in control as a researcher, and not up to some, for instance, unit root tests that you're not really sure if you can actually trust them. One final comment is that while we focus on Granger causality, in fact, what we do here does apply to other forms of inference on VAR parameters. So if you have other hypotheses that you want to test on the VAR parameters, it equally applies, as long as the parameters that you tested on is a small group. So what it definitely does not apply to is impulse response analysis, given that the impulse responses depend on all the VAR parameters, and that is not covered by our methods. The paper is available on arXiv, and we also have an R package available that you can find on Luca's GitHub page. All right, let me wrap up here.
Okay, thank you so much, Stephan. I will stop the recording and we can move to the chat.